So as we discussed last time, Newton and Leibniz each had their own notations for indicating derivatives. The prime notation came from somebody else entirely long after those two were dead, Lagrange in France. Leibniz's notation is one that we're going to look at now. Newton's notation with the dots above the functions really didn't catch on so well. So let's do a specific example to illustrate this Leibniz notation. Suppose we have a function y equals f of x equals x squared. Last week we computed that its derivative is 2x. So last week we could have written the derivative as f prime or y prime. We still can, we still will. But Leibniz notation reminds us of where this derivative came from, namely by taking a change in y over a change in x. So Leibniz would write dy and then a horizontal bar dx. And typically when people read this, they just read dy dx. They don't even say over. So this is another way of writing the derivative. So all of these things equal 2x. F prime of x, y prime, dy dx, they all equal 2x. The thing about Leibniz notation is that it reminds us of where this thing came from. However, this symbol is one single symbol all by itself. It is not a true fraction. This is the actual derivative, 2x. It is not a fraction. It reminds us of where the derivative came from, namely by taking change in y over change in x. But then we took the limit, right? And in the end, we got a formula. We didn't get a fraction. 2x is not a fraction. Dy dx is not a fraction. Similarly, last week we would have written something like f prime of 3. We could have written y prime of 3. We didn't. So how are we going to write this with Leibniz notation? In this case, Leibniz notation maybe isn't quite as nice because it's not clear where you're supposed to put the 3 here. But if I want, if the way that we do it is we draw a vertical bar here. And a single vertical bar in math usually means, not always, but usually means evaluate. And then we tell where we're going to evaluate it. So this is dy dx evaluated at x equals 3. So all of these three things mean the same thing. They mean plug 3 into this. Therefore, they all give us 6 as the final answer. That's what those are all equal to. And then last, we have the symbol for actually taking a derivative. Dy dx is the actual derivative, as is f prime. But the prime symbol all by itself is in math language, it's called an operator. It says, take the derivative. So in Leibniz notation, if I wanted to write take the derivative of x squared, we would write just a d dx out front. So this says take the derivative of x squared. This says take the derivative of x squared. They both give us an answer of 2x. And again, this is not a true fraction, right? D over dx, this is all one thing together. It's easy to get confused between the dy over dx and the d over dx. I like to make an analogy with parts of speech in English. Dy over dx is an actual thing. It is like a noun. D over dx, as we said, is what's called an operator in math. It's telling me to do something. D over dx is like a verb. So dy over dx is the actual derivative. D over dx is the command to take the derivative. Similarly, if you say like square root of x, that's a function. If I just write that symbol, well, you have some idea about what that symbol means, but it is not an actual function, right? Because there's no variable inside of it. This is an operator saying take the square root. And this dy over dx notation was developed by Leibniz in 1675. And we'll get plenty of time to practice this as the semester goes along.